Okay, so now comes a really kind of maybe surprising, I don't know, because everything can surprise us because we are not understand what's going on with it. But maybe a surprising thing. So maybe just recall that if you know that omega is in omega of some b, that just means that omega vanishes on lambda b plus f for that particular b. And so if, as I said, if a is smaller or equivalent b, then omega also is there. Omega lives also in omega of a. Right, so if you take your b and decrease it, you decrease this set, and therefore you make it easier. You have less constraints. So in pictures, what happens is the following. If you know, so these are all the divisors in the world, in your world of f over k, and you take a divisor, if you have an omega in mind, outside of this world, and you know that omega is in omega of b, right? So you know that omega is in omega of b. Well, what I'm saying is that it's also here. It's in omega of every a that's smaller or equal than b. Right? I mean, once you know that omega sits in capital omega of b, it sits in capital omega of everything that below b in the partial order of divisors. And potentially it could have been like, the picture could have been like that or something. Could have been there are several like maximum, but there isn't. So it turns out that there is a unique divisor, let's call it b for a second, that determines whether for every, I mean, it serves as an entry ticket. There is a unique divisor that is maximal in this sense. Namely, if a divisor A comes and he asks whether omega is in its capital omega, then you just need to compare itself with B. I mean, this is the picture. There is a maximal divisor for which omega is in omega in B of B. That's what I'm saying. I'll write it down, but that's what I mean. So the picture is actually nicer than it could have been. So there is some structure here.
Every other A.
Yeah, right. So there is a maximal. So let me write it down and we'll see. But I think the picture helps. Well, maybe together with the statement, but the picture also helps. So for every non-zero divisor, differential, there exists a unique. Unique is actually okay. Let's see. Unique B such that okay, so for every divisor, differential, there is a divisor, it's unique. The fact that it's unique is actually not surprising at all once you know it exists. But there is a unique divisor such that if another divisor comes along, like any divisor now, and you want to understand whether omega sits in the capital of omega of that divisor, you just have to compare it with B as a divisor, which is exactly this picture. So there is a divisor such that everything that's below it, all A's that are below this divisor B, contain little omega in their omega space, and only them. Right, so this is the picture. For every omega, there exists a B like that.
Maximal?
It's going to be, yeah, it's really a maximal, we'll see in the proof, but it's maximal in this sense, right? It's the maximal divisor in partial order that contains such that, you have to say so many words, such that omega is contained in the capital of omega of its divisor. So it is maximal. No, but it's not only maximal. Nothing incomparable to it also contains little omega, only those that are smaller than it. Potentially, there could have been several maxima. And we denote this divisor. I mean, it's the unique divisor, so you can give it a name. It's a unique, given little omega. It's a property of little omega. So we denote this divisor, and that's kind of funny, like that. It's like the principal divisor of the differential, right? It's almost like a comedy, right? It's like you have this for functions, and now you have this for differentials. And that's because if you really understand differential, it's in a sense a function. Like it has a poles and a zeros. That's actually the poles and the zeros that come in this divisor. Right, so actually once you know that, you can think, even if you don't understand anything, you can think of omega as a function, at least in the sense that you know it's zeros and poles. And actually once you know the function zeros and poles, you know the functions up to a constant. This is in the homework question. So that's amazing. That allows you to think of omega as a function. Yeah. So is the statement clear? Right, for every divisor, I can't say it correctly. For every differential, there is a unique divisor that kind of determines membership in omegas. For every other divisor. Just, it's like the guard at the door or something. If you want to figure out whether omega, you see, you don't have to talk to omega, you talk to me. Like, so if you want to figure out, B is like encodes omega. So to figure out whether little omega is containing your omega space, just talk to B. But of course, B is a function of omega, and it's not like that. So yeah. So let's see that. So really, right, so good. So the proof strategy is essentially what you said. I mean, if there is such a thing, it's going to be like maximal. And so you want to take something large, like, something as large as you can. And large in what sense? So we only have like, so you have the partial order, but it's not fun to work with. And we also have the degree and the dimension. So let's try to, so the first attempt, it's a good attempt. It's not the first attempt. What we'll do is we are going to take the divisor of a maximal degree that satisfies that. I'm going to take a divisor of maximal degree that omega is in its omega space. But for that, we need to prove the degree is bounded. Like, who knows? So this is what we are going to do. So take any A, consider any A, that's kind of a candidate for being B actually, but I don't want to call it B yet. So consider any A, any divisor that contains, let me write it contains omega, instead of it's omega space containing omega. So let's take any divisor that contains omega in this sense. I want to show that A has a bounded degree so that I can take the max one. So by Riemann's theorem, the degree of A, sorry, the dimension of A, sorry, no, that's, I skipped a step. By some claim. By claim, the last claim that we proved, claim 18, the dimension of A is at most G. Right, this is actually appear here, that's the end of the proof. So we said, if your omega space, if this, your it's the divisor, if the omega space of a divisor is not empty, and omega is not empty, it's not containing only 0, and omega is not 0, then it can't have a large dimension. Right? Because that's what we proved. We compared that against omega of 0 in claim 70. We proved that. And then, but I don't want to talk about dimension. I want to talk about degree. It's easier to work with later. So by Riemann's theorem, we have a bound on the degree also, right? So the degree cannot be much larger than the dimension, at most by G minus 1. Right, that's the deficiency. So you can't have a very high degree and very small dimension given a genus. So the degree is at most 2G minus 1, like G minus 1 more than that. Good. So now we know that any candidate for B, so we know that if, out of all of the divisors, if you split them according to degree, then when the degree is too large, more than 2G minus 1, in no way, all the omega spaces are just empty. So they contain nothing. So really, what we are going to do is just take the maximal degree divisor. Now it's well defined, such that little omega is in capital omega of A. We now call it B. So let's do that. So let B be such that omega is in omega of B. So I'm going to choose a divisor satisfying this of maximal degree. And potentially I could choose one, like, potentially there are more than one. But that's a good candidate. If there is a candidate, it has to have maximal degree. So that's the only chance it will hold. So now let's see. So now, okay, so now we have it. And now let's see what happens here. So take any A now. So take any divisor such that omega is in its omega space. And I want to show that indeed A is smaller or equal than B. All right, that will prove this direction. That direction is obvious. Because we said that if B is larger than A, then omega is also contained omega of A. But the non-obvious direction is this one. Right, so all I know about A is that it is this thing, that it contains little omega in its space. So why should it be smaller or equal than B? So let's see. So we know that omega is in omega of A. That's what A did. And it's also in omega of B, of course, because of that, which is equal to, and here we need the equality. One of the properties that we didn't prove is the omega is equal to the omega of the maximum. Oh, but that's weird, right? Because this is larger than B, like generally speaking, unless A is smaller than B. Right? So from this we know, let's do it formally. So from this we know, I mean, generally we know, or maybe from this we know. Okay, let me go back. Let me fix one of the arguments. So by the maximality of B, we know that the degree of B is larger than the degree of, which is weird, the degree of the maximum of A and B. That's not natural. But that's maximality of B, right? I mean, this is a divisor whose omega space contains this omega, and B was chosen a divisor of maximal degree that does that. So that holds by maximality of deg B, of the degree of the divisor they choose. But that's that's impossible. I mean, that means that B is max AB. Right? I mean, every entry here is smaller or equal than every entry here, and yet they have the same degree. So they have to be the same, point-wise. Like, no way there is a gap. And this is larger or equal than A by definition, which is what you wanted to prove. Yes.
This is like the sum for the degrees, right?
Yeah, like, yeah, right.
Larger than something, maybe like the
Right.
other,
You're right, but this is B compared to max of AB. Right? If I know that deg B is larger than deg C, I don't know that B is larger than C. But if I know that deg B is larger than deg of max AB, right? Yeah. Yeah, that's cool, right? I don't know. Yeah. So we have that. That's the proof. I mean, I need to show if and only if, but that direction is obvious. So if you know that, then you know that omega is in omega of A because it's in omega of B. Yeah, good. So now comes even a kind of a more, or I don't know, surprising thing. So now that we have this divisor of a differential, right? So think of the hierarchy. You have functions which you kind of think you understand functions in F, but it's not so easy to understand. These are a complicated feature because it sits on a curve and there are algebraic relations. But functions we got used to. Then there were Adels, and then there were differentials, and then we took a divisor of a differential. So we really want to get a handle over this thing. I mean, now you see, now you took, I mean, you go down. It's like Adel are complicated, omegas are even more complicated, essentially by definition. But then divisors of that, as a creature, it's a simple type, it's a divisor. So maybe you can understand the divisor of a differential, even if you don't quite understand the differential. Right, so this is what's going to essentially happen. So claim 20 says that for every non-zero differential and x function, non-zero function, so yeah, this holds, which looks very natural until you think what's going on here, right? So omega is a differential, so this is something we don't quite understand. It's a weird creature, like differential divisor of a differential. this is the plain old principal divisor of a function. That's why I wanted it to be non-zero. I don't want to look at zeros, of course, also here. But then what I'm saying is that if you remember, we know how to multiply an element, a function with a differential. And what I'm saying that things are kind of consistent. So the divisor of that differential is what you would have expected. It's like if this was a function that holds, right? We know that the divisor, the principal divisor of x times y is the sum of the principal divisor. So the same holds for this other type of differentials. Okay, it's kind of weird. And the proof is as follows. So let me write the following. So forget about that for a second. So let's look at x omega. So x omega, so for any divisor A, okay, which doesn't appear here at all, I'm just saying for any divisor, x omega is in omega of A if and only if omega is in x minus 1 of omega of A. Right, so forget about the whole theorem. Just saying that, generally speaking, for every divisor, x omega is in this capital omega space of A. Is just saying you can just move the x minus 1 here, is in omega of that kind of shifted version of the omega space. We know that that's the same thing as, I mean, we know that this is a set, is omega of some other divisor, right? So this is the same as saying like that omega plus a minus x is larger than 0. Right? That's when an omega is in a lambda space of a divisor. It's like in a Riemann-Roch space, but with omega, with alphas. No, I did something reversed. No, sorry. No, that's completely, sorry. So by the previous theorem, by theorem 19, that was so bad. By theorem 19, that's the whole point. Like this arrow is the whole point of the proof. By theorem 19, we know that for omega to be in an omega space or something, right, the ticket is you need to compare that divisor to what we define to be this unique divisor, which we denoted by brackets omega. So that's equivalent by definition of this thing using this theorem, which allowed for the definition to that. That's exactly that theorem. That's if and only if. B is a minus x, and I don't know. No, a is a minus x, and B is this thing. Right. That's for omega to enter an omega space of a divisor. You need, according to that theorem, to compare that divisor to the divisor of omega. Right? That's fine. Right? And that's the same thing as saying that A is at most x plus omega. Just moving things around. These are just divisors, you can move them around, that's fine. Right, so what happened here? We use theorem 19 to prove that for any divisor A, and you should compare it to that again. Now look again at theorem 19. So for every divisor A, x omega is in capital omega of A, if and only if omega A is smaller or equal than this divisor. But theorem 19 tells you there is a unique divisor that does that. You can't have two bodyguards at the end of the club, right? You have like, this is done by x omega. So by theorem 19, again, not another implication of theorem 19, tells you that this is equivalent for every A to saying that A is smaller or equal than x omega. That's what theorem 19 told you. It took, if you want to enter the omega space, you need to compare yourself to the divisor of the differential. So this means that this must be that divisor, because you have two if and only ifs, and it's a unique divisor. Oh, I didn't prove uniqueness, by the way. I forgot. But uniqueness follows because you can just, right? You can do this and then that. Anyhow. So, good. So that tells you that this divisor, which is the divisor of this differential, is actually what you may have wanted, even if you don't quite understand what is the differential divisor of a differential. Yeah, good. Questions?
What just showed like the kernel that like all of the advantages and stuff like that, or all of the defined areas, dimensions, are actually every dimension has some divisor that correspond to it. And you just ask the same question about the dimension. The same question as the dimension, the divisors, right?
Right. Yeah. So right. So what you're saying is that now, if I understood correctly, you don't quite understand differentials, maybe. So you want to translate questions about them or to understand them according to divisors. Right. So the first thing you have to understand is what are the divisors coming from differentials, right? Because it's not maybe not all divisors. I mean, actually, that's right. Right. Yeah, we are going to see exactly. Yeah. That's the thing. But yeah, that's true. That's exactly what we're doing. We understand this differential using this divisor. Yeah, very good. That's exactly what's going to happen now. A definition and a claim. So yeah, very good. So a divisor of the form, a divisor that comes from a differential. Omega, or some omega, maybe I should say non-zero or something. Because then it's called, it has a funny name, canonical, even though there's more than one. So it's not that, it's a kind of a bad naming. It's not that it's canonical. But you'll see 1 second something about the canonicality of those. And this set, just words here, definition, the sets of all canonical divisors is denoted by this cool W. I don't know. It's not, that's not cool. W. Yeah. I don't know how to do it. I'll just try to really copy it. I don't know. Okay, it's a W. It's cool W. You can see in the notes. And okay, that's just the definition, but the claim will gives you more information. The claim says that this W is an element of what we looked at. If you remember, these are all divisors, and this is the principal divisors. So what I'm saying is the W is one class there, is an element. That's why it's called canonical. All divisors that come in from differentials, all canonical divisors, form one class in this quotient. Namely, for every two divisor, the difference is a principal divisor. For this is P. Sorry. Yeah, principal. These are all divisors, these are the principal. That's 1 or 0. Yeah. Right. So that it's. So I mean, when we say canonical, what I mean really is that it's a canonical class. There is one class. All differentials are kind of can be represented by one representative or something. So the proof is actually kind of. I mean, this is really the proof. So like this is the heart of the proof. So the proof is as follows. So take any non-zero divisor, differential. Now, here I think it's the first time we are using the one-dimensionality of omega over f. So by theorem 16, which you didn't prove, and it's in the videos, omega is x omega when you iterate over all x and f. Right? It's a one-dimensional vector space over f. So once you fix one omega, which is non-zero, all the rest is like a line in a sense. Through that, and so let's see. So this is W. I don't know why I have like a. Yeah, okay. So this W, right, by definition, is just the set of all divisors coming from differentials. And I don't use this omega, I'm using a general omega prime because this omega is a fixed omega. Right, this is the set of all canonical divisors by definition. But according to that, every omega prime is actually x times our omega. It's kind of one-dimensional. Right? That's really this. And then according to, so that's theorem 16, or that. And then according to this, I can split x omega to x plus omega. Maybe I write it omega plus x. But then you see that we are done. Because this is, I mean, this is independent of anything. So it's omega plus this set, which is exactly the set of principal divisors, P. So, yeah. So it's one class. Theorem 16 is this one, actually. Yeah, so this is claim 20. This is set theory. Yeah, good. Questions? Yes.
So what we showed here is that, so how do you think about what we showed here? That actually the functions are not that large, are just one offset.
Right. So if you consider like, that's the right question. So when we look at these things, I mean, why do we look at that? Because essentially everything we care about, degree and dimension so far, and also everything that has something to do with it, like index of speciality and so forth, is not a property of a divisor. It's actually a property of this thing. So the principal divisors are not, it's a noise. It's not really important. So what that it tells you is that, I mean, if these are the elements you care about, then a differential is just an element here. Right, right, there is, like, all differential is just one element there. We'll see soon, like, more about it, but like now, essentially.